Hello, and welcome to Lesson 4 on this course on metric and topological spaces. In this lesson, we're going to be introducing the idea of a metric space and the idea of convergence within a metric space. As always, the booklet is in the description for you to follow along with and then do the homework questions at the end, and the answers are also in the description. So what is it we're trying to do with metric spaces? So the whole point of a metric space is to generalize the idea of distance. So here we've got 2 points. So let's look at the properties of the distance between them. So if we try to measure the distance from one point to the other, well, the first thing that's apparent is unless the 2 points are exactly on top of each other, this distance has to be greater than 0. Secondly, the distance is the same if we measure from the left point to the right point or from the right point to the left point. And then finally, if we have a third point, and if we measure the distance from that first point to that third point, and then the third point to the second point, that has to be longer than just going in a straight line from the first point to the second point. So we've got 3 properties here. Firstly, the distances between different points is greater than 0. It doesn't matter whether you measure in one direction or the other, so it's symmetric. And finally, if we measure the distance going in a triangle here, that has to be greater than just measuring in a straight line. Now that's fine if we're just looking at points on a surface. However, we want to generalize this. So what does it mean? How can we measure the distance, say, between the functions x squared and 5x? Is there any way we can make sense of that? And we'll see that maybe we can do. Now we're going to look at the definition of a metric space. Let A be a set, a function d that maps A cross A to the real numbers is called a metric if, for all points x, y, z in A, we obey the following axioms. And very quickly, this A cross A notation, what that means is that d, the distance function, takes 2 arguments. So we have to obey the following 3 axioms. Firstly, it's the positive definite axiom. So that is d of x and y has to be greater than or equal to 0, where it's only equal to 0 if the 2 points x and y are equal. And this must be true of any 2 points x and y in the set A. Then the second axiom is the symmetric or symmetry axiom, and this is just saying that d of xy equals d of yx. So this means it doesn't matter whether we measure the distance from x to y or we measure the distance from y to x. And then finally, we have the triangle inequality, and that's just saying that the distance from x to z must be less than or equal to d of xy plus d of yz. And then a metric space, AD, is a specification of both a set, here given by A, and a metric D. And often the metric or the function D is sometimes called the distance between the 2 points. So you might hear me use that term interchangeably with metric. Let's look at some key examples of metric spaces. Now these examples will come up a lot throughout the next few lessons, and it is really useful to try and get a handle on all the different theorems we come across. So our first key example is what's called the discrete metric, or sometimes called the trivial metric. So let A be a set, then define the metric on A as d of x and y is equal to 0 if x equals y, or 1 if x is not equal to y. So it's just 0 or 1. It's 0 if the 2 points are the same point, and it's 1 if they're different. Okay, so let's look very quickly at calculating some distances with this. So if A equals n, so that's the set of natural numbers, find the distance between 2 and 7. Well, 2 and 7 are different, so the distance between them is 1. And then the distance between 5 and 5, I'll give you kind of 5 seconds or so to think about it. Well, 5 and 5 are the same point, so d of 5, 5 is 0. We still need to check that this is a metric, so we still need to check that this obeys the 3 axioms from the previous slide. And I've put that in your booklet, so pause the video and have a read through that. We go through and prove that this does obey each of the 3 axioms. Our next key example is what's known as the Euclidean metric. And the Euclidean metric is just the normal way you would measure distances using Pythagoras' theorem. But it's also an example of a metric. So we define the metric d on Rn via d of x and y is the square root of the sum of xi minus yi squared. So here Rn is just n-dimensional Euclidean space, and the points xi and yi are just components in either n-dimensional points or vectors. Okay, so in 2D, so we're going to just say n equals 2 there. Find the distance between -2, 5 and 1, 1. Right, I'll give you 5 seconds, 10 seconds for you to have a think about this, and then I'll put the answer up. Okay. So you see, it's just like normal Pythagoras' theorem. If this was higher dimensional space, you would just have to include more terms. Okay, then the next example, I'll give you a few seconds to think about it. Okay, so the answer here is 3 root 10. And again, even though this was our kind of motivating example, to be strict, we still need to check that it does obey all the metric space axioms. And again, that is in the booklet. In general, whenever you're given a metric, it's good to check. We're not going to check all the metrics we see in the video because that would take too long and some are much harder to prove. But it's always good to think that you need to check that these things are actually metrics. The Euclidean metric is not the only metric available on Rn. We could obviously have the discrete metric, that works on anything. But there's another class of metrics we can use. So we have the metric on Rn, and this is defined via here. So this is very similar to the Euclidean metric, except we take the pth power, and then we take the pth root. So, with these metrics, find the distance between -2, 5 and 1, 1. So for p equals 1, I'll give you a second to think about it, or a few seconds to think about it, and then come back to the video. Okay, so if we're just taking the first power, then we're not doing it to the power. We're not taking the root, so we just add together the absolute values, and we get 7. Then p equals 2. I'll give you a few seconds to think about it. Well, for p equals 2, we're squaring and then taking the square root. So that is just the same as the Euclidean metric. And then finally, p equals 10. For this, we take the 10th power and then we take the 10th root. The answer is 4.02. There are loads more decimals, but I've just rounded it. You may have spotted a little bit of a pattern as we were increasing the value of p. And there is a pattern in the way these metrics behave. So what I'm going to do is I'm going to put up plots for all the points that are at distance 1 from the origin. So for the where p equals 1, all of these points form a diamond or a rotated square. And you can verify that everything on here has a distance 1 from the origin. For the Euclidean metric, it's maybe exactly what you'd expect. Everything that's a distance 1 just forms a circle. Then as we increase p, so if we go to p equals 10, we find it forms more of a square shape. And again, you can verify this yourself. As we keep increasing the value of p, it becomes an almost perfect square until we get to, as we go to infinity, the limit of all of this is we take the maximum value. So the infinity metric is the maximum absolute difference between each of the coordinates. And when we do that, we see it forms a perfect square. We're now going to look at metrics on a space that maybe you wouldn't have considered you can easily measure distance in, and that is the distance between functions, or the distance between continuous functions. So if C is the set of continuous functions on the closed interval 0, 1, so that does include 0 and 1, and let f and g be just arbitrary functions for this. And note that continuous functions on closed intervals are bounded, so they never go to infinity. If we'd had an open interval, then they could tend to infinity as we get to the edge. If you haven't seen that, don't worry. Just remember that these functions don't go to infinity. So our first metric, called the L1 metric, is we take the absolute value of f minus g and we integrate it over the domain. You may have seen a similar metric when dealing with quantum mechanics, where you take the square of the functions and integrate it. It's a similar metric, slightly different. And then a different metric we could have is the supremum metric, which looks at the maximum value between f and g on that interval 0, 1. And supremum here just means the least upper bound or the maximum value. Okay, find the difference between f and g, where f and g are given on screen, and you see I've plotted f and g there, so you can see them. All right, have a go with the L1 metric, and then come back to the video. Okay, now you've had a go with the L1 metric. I'll go through the solution. So we want to integrate f minus g. However, since f is smaller than g, we take the absolute value, which is the same as g minus f. Then we integrate that, and we evaluate it at the endpoints, and we get 2/3. Now have a go working this out with the supremum metric. Okay, now you've had a go. We need to notice that the maximum value of f minus g, in our case, is at x equals 1. It's not necessarily always going to be in the same place. You may have to differentiate. It may not be easy to spot, but in this case, it's just at x equals 1. And at that point, the distance is 5/4. Another space we can define metrics on is the space of convergent sequences. And you'll see why they have to be convergent in a bit. So let A be the set of all sequences of real numbers, which we denote the whole sequence in brackets and then with a subscript r, or to be fair, any subscript, such that the sum of xr squared converges. That's, if we take every element in the sequence, we square them, and we add them together, then that sum is finite. And then a sequence, if you haven't seen that before, is a countably infinite set, or countably infinite list of numbers. So x1, x2, x3, and this goes on forever. Alternatively, you can think of it as a map from the natural numbers to, in this case, the real numbers. But you could have sequences of complex numbers or other things. The point is, it's just an infinitely long list. Then we're also going to say let x and y B sequences, where X and Y both denote the whole sequence. Then we can define different metrics on this. The first one we can define is a little bit like the Euclidean metric. So we sum up, we take the difference of every individual element, square it, add them all up, and then square root it. And this is why we needed the sequence to be convergent. If the sequences weren't convergent, then this sum here might not converge. And then this whole metric wouldn't be well defined. Alternatively, we have the supremum metric. So we take the maximum difference of all the different elements, and then the biggest difference is the distance between the two sequences. We're now going to look at a couple of examples where we build a new metric space from an old metric space. Now, sometimes this might be obvious, but in some examples there can be a little bit of nuance. So the first example is a subset metric. So if AD is a metric space and S is a subset of A, then we can define a new metric, D sub S, which we can sometimes call the subspace metric or the subset metric. And we define this via D sub S of X and Y is just equal to D of X and Y for any 2 points in the subset. Now this may seem kind of obvious that we haven't really done anything, right? We've just taken the 2 points and we've just used the original metric. But the reason I'm being explicit with this is that sometimes when we look at subsets or subspaces, things get a little bit tricky. And we'll see that when we do subset topologies later on in the course. Okay, let's have a look at a quick example. If R squared D is a metric space where D is the Euclidean metric, using the induced metric on Z squared, find the distance between 1, 1 and minus 3, 2. Well, we just do this the normal way. And we get root 17. We're now going to look at metrics on a product space. So if AD and BD prime are both metric spaces, we can define a new metric on the product space A cross B, which we're going to call capital D. And we're going to define this via D. So capital D takes 2 elements. So the first one is A1, B1, where A1 is in A and B1 is in B. And then the second thing it takes is A2, B2, where A2 is in A and B2 is in B. And then this metric is given by the maximum value of both metrics, where D just acts on A, so it just looks at the distance between A1 and A2, and D prime just acts on B. So that just looks at the distance between B1 and B2, and then so we compare both of these and take the maximum value. Okay, that's maybe a little bit confusing, but I've got some examples. So let A equal R squared, and that's equipped with the Euclidean metric, and let B equals N, equipped with the discrete or trivial metric. So I'll go through the first one and you can go through the second one. So firstly, let's find the distance between 0, 0, 0 and 0, 0.5, 0.3. Where for these, since A is R squared, the points 0, 0 and 0, 0.5 are both in A, and 0 and 0.3 are both in B. So let's find the distance between these. Firstly, let's look at D. This is the Euclidean metric between 0, 0 and 0, 0.5. So we work that out as normal and we get 0.5. Then we look at D prime between 0 and 0.3. And because this is the discrete metric and those points are different, we just get 1. And so the product metric takes the maximum value of these, and that is just 1. Okay, have a look at these next points and have a go on your own, and then I'll put the solutions up on the video. Okay, now you've had a go. D of 0, 0.5 and 1, 1 gets you about 1.12. And then D prime, those points are different, so we get 1. So therefore, capital D of these 2 points is 1.12. And note that both for product spaces and subspaces, these induced metrics are not the only type of metric you can define, but it's one that you can always define if you don't know what else to do. There's always often other possibilities, but this one is one that always works. We are now going to look at the notion of convergence within a metric space. So we're going to look at a sequence of real numbers, and they're going to be, as always, indexed by the natural numbers. So on the y-axis here, we have the real numbers, so this is the space we have a sequence in, and the x-axis is just a way to index the elements of the sequence, and they're indexed by the natural numbers. So let's look at what our sequence is. So second point, third point, and so on. And we can see that our sequence gets closer and closer to 0. So intuitively, this is converging to 0. It's getting closer and closer. But what's a way we can formalize this idea of getting closer? So if we look at a particular distance away from 0, so that's represented by this line that's just come up, well, every element from the second element onwards is closer to 0 than that line. Then, if we go even closer to 0, we get the same thing. So here we're even closer to 0, and we see that every element from the sixth element onwards is closer to 0 than that line. And this goes on. If we want to look even closer to 0, we'd have to find a much bigger element for down the line in the sequence, but everything further along than that would be even closer to 0. We're now going to look at the proper definition of convergence. So if AD is a metric space and AR is a sequence of points in that metric space, the point A is a limit point of the sequence AR if the limit as r goes to infinity of the distance between A and the point AR is 0. So in other words, if the distance between A and AR gets closer and closer and closer. In this case, we say AR converges to A, or we can just write an arrow. So AR goes to A. Now, an equivalent definition, if you're not super comfortable with dealing with limits, is, so the point A is the limit point of the sequence AR if for any epsilon greater than 0, there exists an n such that for all little n greater than big N, the distance between A and AN is less than epsilon. So this goes back to our diagram on the previous slide. No matter how far away you want to look, no matter how close to that limit point you want to consider, you can always go far enough in the sequence so that all points are that far away, or at least that close. And note that for this definition, we do need to know or suppose or guess the limit point in advance. This doesn't necessarily tell us what the limit point is. But once we found it, we use this definition to check. We're now going to have a look at a couple of examples. So for our first example, the space is r squared and the metric is the Euclidean metric. And we want to ask or check, does the sequence defined by 1 over n and 1 minus e to the minus n, does this converge? So firstly, we have to work out what the limit point is. And looking at this, I'm just going to make an ansatz that it converges to 0, 1. So let's check this. So firstly, we're going to take the distance between a point Sn and the point 0, 1, and that's given by this. And then we want to see, does this go to 0 as n goes to infinity? And indeed it does. 1 over n squared goes to 0, and e to the minus 2n goes to 0. Okay, so we've got another example in the metric space C, dl1. So that C was the space of continuous functions on the domain 0, 1, and dl1 was the metric defined by the integral of the absolute value of the difference of the functions. And then we have a sequence defined by f sub n is given here. And what this is just like a bump between 0 and 1 over n, but the function is 0 otherwise. And then we're asking, does this converge to 0? Or the function f of x equals 0. So have a go on your own, and then come back to the video and I'll go through the solution. Okay, let's have a go. So firstly, we want to calculate the integral from an arbitrary fn to 0. So it's just the same as integrating fn, and it's positive everywhere, so we don't need to worry about the absolute value. And also notice the limit goes from 0 to 1 over n. That's just because the function is 0 after that. So we calculate this integral and we get 1 over 6n, which converges or goes to 0 as n goes to infinity. Now, what if we had used the supremum metric instead? Again, I'll give you a few seconds and then you come back to the video. Okay, well, now you've thought about it, the maximum value between fn and f is always a quarter. In order to find that, you may need to differentiate or complete the square or something to find where the maximum value is. But because this is always a quarter, it doesn't converge, it never goes to 0. We're now going to look at some properties of limits. The proof for these theorems are in your booklet to work through and read through, but I'll put the statement of the theorem here and give a rough explanation. So firstly, the limit of a sequence is unique. That is, if a sequence converges to a point A and to a point B, then those 2 points must be the same point. And really the reason for this is that the distance between any 2 different points is never 0, is always greater than 0. Therefore, if a sequence converges to 1 point, say point A, then the distance to point B obviously can't converge to 0. Then our second theorem, for any convergent sequence, all subsequences also converge. So a subsequence is we just take the original sequence and we delete or remove some elements. So a subsequence is also a sequence where all of the elements come from the original sequence in the same order. All we've done is remove some elements. Because all we've done is remove some elements, the new sequence will also converge.